Um, so the topic of conversation today, I really want to talk about the RAG and the RAG process, but I think it's important to understand some of the technology behind RAG before we jump into RAG. So talking about RAG, Retrieval-Augmented Generation, it's a really cool way to extend the capabilities of large language models by dynamically adding relevant content to prompts. That extra content could be something that's domain specific or proprietary or more timely than what the large language model knows about. I think ChatGPT 4.0 ended in December 2023. So anything that's happened since, you might want to augment with more relevant data. But really, the use cases are more often than anything is using proprietary or custom data and being able to add that context to a prompt without having to paste in all sorts of documents to use as that context. So the RAG process will take a large collection of documents and chop them up into small pieces that can be stored in a database and then used as needed to provide the additional context. And we'll dig into what that looks like and behind the technologies that allow RAG to happen. So I've got a dozen or so slides here. I'm going to go through the slides and then jump over to a Jupyter Notebook, which is an interactive dynamic environment that allows me to present text and code and run the code and show you the results of the code. So we'll have a interactive live demonstration of how to use the things like vectors and embeddings, and then ultimately a couple of examples of a RAG pipeline to go through. Should be fun. Hopefully everything goes smoothly. If not, I do have a backup plan. So we should be fine. So just quickly, some of the things I want to kind of tee up in the slides here is how, at a very high level, how neural networks work. And then we'll get into vectors, vector databases and embeddings. So I may not tie it all together here in the slides, but when we get into the Jupyter Notebook and I start presenting some visualizations, I think that'll help pull it all together for people. So the way neural networks work is there's a select set of input neurons, then there's the intermediate neurons or hidden layers and output neurons. I often refer to the neurons as nodes. Kind of goes back and forth, but there's a a similarity between how how neural networks work and how the human brain works. So there's often used some terminology that's similar to brain. So neurons is often used. So the neuron is or node is a processing step, and you'll see the little green and yellow dots. Those are weights on the relationships between neurons in one layer and neurons in the next layer, and it's those weights that get tweaked and adjusted to allow the model to learn, and they represent the strength of the connection between those neurons. So all of the neurons in the input layer is connected to all of the neurons in the next layer down, and then so on. And each layer is connected to all the neurons of the next layer. You start with randomized weights, and then start training the data by passing in inputs into the input layer, passing it through the network, and getting an output as a result. You then compare that output to what you expected the output to be, and feed the difference between the two back through the network in the reverse direction through a process called back propagation to adjust the weights. And then you do that over and over and over again with large sets of data to train the model and reduce the error rate. And the way this works, you can think of the input neurons as taking inputs from an image, such as a bird, and each of the nodes. Is there a question?
Yeah, David, sorry for the interruption. My first question is, do we want to allow for questions during the presentation? And if we do, there is a small one. Ken is just trying to understand when we're talking weights, how do you spell the word weight?
Spell the word weight. It's WEIGHT.
GHT, thank you.
So it's a numerical weight, and I'll show an example of it's actually a floating point value
Thank
um,
you.
that numerically represents things. So one of the ways you can think about how the neural network works is a lot of this work for creating neural networks was done on image recognition. So it's good to kind of use an image, maybe of a bird. This is from the meetup group kind of image. And then each of the input nodes is 1 pixel, represents 1 pixel of the image and the brightness of that pixel. You can then pass that data through the model, and each layer is looking at for different attributes of the image, different images, edges of things in the image. So it could potentially pick out an angle of a beak or the circle that represents an eye and start to understand that this is an image of a bird. And it passed through, and if it said this is a bird and you were expecting bird, then you can start reinforcing that that is the actual case, and you've got a good training method. So that's just really high kind of overview of how neural networks work. And there's some limitations to it, though. Neural networks are great for that point in time. You got one image that you want to process and identify something in the image, or maybe you want to take in a word and try to predict the next word, but that's really hard because language is really complex. So this kind of point in time use of a neural network doesn't lend itself really well to natural language processing. Because you could feed in the word cat, and then what you're going to get out at the other side, you're not quite sure, because cat can be used in so many different contexts, whether it's dog and cat, or maybe cat is representing the company Caterpillar or an abbreviation for the word category. So you need to know a little more context. And the way that this has been solved is by using a transformer architecture. So the transformer architecture, and again, very high level kind of concepts here, was introduced by Google Research in a paper titled Attention is All You Need, that they published in 2017. That really kicked off everything that has become, the modern generative AI movement. And it works through a combination of things. So there's positional encoding. You take a sentence and you tag each of the words in that sentence with where they appear in the sequence of the sentence, which then unlocks the ability to do parallel processing. So you can process each of the words because you know the position of that word in the sentence. You can now process them in parallel, which speeds things up dramatically. And then the big kind of benefit, or the big kind of thing that really makes it all work, is a self-attention mechanism, which allows the model to understand the importance of each word in relation to other words in the sentence, even across long distances. And what we mean by long distances here is, something could be at the beginning of the sentence that's impacting something further on in the sentence at the end of the sentence. So if you look at, kind of extending that cat conversation, is the cat jumped onto the couch, is, cat is very different than the doctor ordered a CAT scan to assess the injury. So the self-attention mechanism really helps encode the meaning of the word cat in all its various forms, and so that when we're trying to generate text, we can do that more easily. And the process that's used to do that is called contextual embedding. So the words are converted into context-aware numerical representations that capture the nuances of the meaning of the word in multidimensional space. Now, I'm going to get into this a little more deeply, so don't worry about it right now. But this is how the transformer architecture is working. It allows for that positional encoding, parallel processing, self-attention, and embeddings. All right, so now I'm going to just take a step back. Let's take a look at kind of some of the inputs to the process. We kind of define some terms, and then I'll jump over to Jupyter Notebooks and help you understand better what's happening with vectors and embeddings. So structured and unstructured data. Structured data, data stored neatly in spreadsheets and databases, has a predefined structure, fits neatly into columns and rows. This is the traditional data that computers are really good at handling. Unstructured data, things like text documents or music, pictures, videos, PDFs, it's harder for computers to understand that the meaning of the text or the picture in this unstructured data. So what we're really looking at is how do we take unstructured data and make it understandable to machines? And to do this, we convert the data into a numerical format that computers can act on and understand. And to do this, we are placing that information into a multidimensional vector space. And so you can see in the little image here, you've got the unstructured data. It's being processed through the embedding process and then positioned in multidimensional space. And the relationship of objects in the multidimensional space provides meaning and understanding. All right, so what's a vector? A vector is an arrow in space that has both direction and magnitude. So this vector starts at 0, 0, goes to 1, 1. It's got a direction and a magnitude. And machine learning uses vectors to represent data, with direction showing the relationship between the data and the magnitude indicating the strength of those relationships. Again, bear with me. This will come together. I promise you when we get into the Jupyter Notebook, and I can show you some better visualizations. So these mathematical representations of vectors help computers to understand and analyze data that's encoded in the meaning of unstructured data. So you can see that here. We've got the light blue vectors representing data that's similar, that's clustered together, where the other vectors are dissimilar, they're further apart. So it's fundamentally, this is what's happening. It's just happening in a much more complex way than in 2 dimensions. The dimensions are much higher dimensionality than represented here. All right. So embeddings are the take the words or unstructured data, and based on the context in which they appear, whether it's in a sentence, a paragraph, or a chunk of text, convert them into vectors that represent their meaning in that multidimensional space. And these vectors allow us to see the relationship between words and understand similar meanings that come from how they're positioned in that multidimensional space. The term embedding comes from the fact that the meaning of the word is embedded in that numerical vector representation. Yeah.
David, so there is a question in the chat. Ken is asking, do we know what does each dimension represent? Is it contextual?
I'll get to that in a minute. But ultimately, we don't know necessarily. We know that it represents some quality of language. We don't necessarily know exactly what quality each layer represents. Let's get into the Jupyter Notebook now, and I can show you some. So we just went through really quickly what neural networks are, the transformer architecture, structured, unstructured data, and introduced the ideas very, very kind of at a not a very granular level, the idea of vectors and embeddings. So really want to now dig into understanding embeddings and vector databases more clearly. And then once you have an understanding of that, understanding RAG and retrieval-augmented generation is pretty easy. So there's a little setup where I imported a bunch of Python libraries and my OpenAI API key. And now let's take a look at word embedding. So start with just looking at one word at a time and positioning that word in vector space by running it through an embedding process. So there's a pre-trained model that we'll use to do this, and it will position the word in a high dimension vector space that we can then take a look at, not try to get an understanding of how it's used. And then to Ken, to your answer, your question, each dimension represents a specific attribute of language, such as maybe gender, tense, or plurality, but we don't really know what's happening in the model. It's all being done kind of automatically through the training process. So we don't necessarily understand clearly what each of the layers is representing, or each of the dimensions. All right, to demonstrate this, I've got a collection of 125 words broken down into 5 different categories. Let me show you what those look like. So I'll pull in this word collection CSV. We can take a look at the categories: animals, colors, emotions, locations, common objects. Take a look at a few of the entries. The first 5, the last 5, we've got cat, dog, elephant, tiger, horse, and some common objects of backpack, notebook, shoe, hat, mirror. We can also take a look at some of the colors, see what they look like: red, blue, green, yellow, purple. So we've got 5 categories with 25 words each. And now we can use those to help understand what's happening with word embeddings. So I will take all of these words, pass them over to the OpenAI model text embedding 3 small, which will return a 1,536 dimensional vector representation of each word. So we've got 1,536 dimensions. If each of those dimensions, some attribute of language. We'll then store those results in a database, a vector database called ChromaDB, which is an open source database and popular for this kind of work. And then it makes it easy for us to then pull that data out as needed and generate some visualizations that I think will really help people understand what I'm talking about here. All right, so here's a function that will take in a word and generate an embedding. And then here's the setup for the ChromaDB to create the Chroma collection that will store the results in. And then here's the code that loops through all of the different words and generates the embeddings and stores them in the database. Now, this is going to take a minute to run. So we'll talk about what I'm going to do next. I wanted to show you how long it takes for these things to process. It's resource intensive. This is sending a word out to OpenAI. OpenAI is taking each word and running it through that model and generating the 1,536 different dimensions for each word. So it takes a minute. Once we have the result of all of that, I'll show you what we get back as a result from OpenAI, and then more importantly, use what we get back to create some visualizations in 1 dimension, then 2 dimension, and 3 dimension. And you'll be able to see how, as you add dimensions, it becomes more understandable how the data is positioned in that vector space, and that it's the similar category data is positioned close together. Unfortunately, there's not a good way to represent 1,536 dimensions, but we can do a few dimensions and then think about how the extra dimensions are adding additional context and information. All right, so the process is done. Let's take a look at what we've got. Here, the first kind of 10 results from emotions just to show we've got in the database now emotions plus some emotions. And we can take a look at, there's a little function to return the embeddings from the vector database for a word that I pass in. So pass in hopeful, and here you go. Those are the, again, the 1,536 dimensions of value between -1 and 1 for that word, which was hopeful, I believe. Yeah, so for hopeful. So this is where hopeful resides in that vector space, that multidimensional space. So that's not great. I can't get, for me, I don't get much out of looking at these numbers. So let's take a look at some representations for the words calm, blue, cat, and tiger in one dimension, where a red value is a high correlation, a blue value is a low correlation. It's hard to get anything out of this. I mean, you can see how the 1,500 or so values are represented here. It's much easier to look at than a string of numbers. But it's hard to see, are cat and tiger similar, or are blue and calm similar? Doesn't reveal a lot of information. It's definitely easier to explore, but still doesn't provide much insight into what's really going on. So let's extend it. Let's take now a look in 2 dimensions. So the first thing we have to do is convert that 1,536 dimensions down into 2D and then 3D representations of the data, and using a t-distributed stochastic neighbor embedding process. I'm not going to go into that, but we're reducing the dimensionality down to 2 and 3 dimensions, and then we can plot it. So now you can start seeing, even in 2 dimensions, you can start seeing the connections of these groupings of words where common objects are grouped together. The emotions in blue are grouped together. And it's a little fuzzier here with colors and animals, and locations have some emotion in there too. So, but at least you can see that, okay, these similar kind of ideas are grouped together in 2-dimensional space. Yes, Natalie.
So another question from Ken. So you are transferring OpenAI's vector space into your local space, or am I misinterpreting? Local model.
So I queried OpenAI to return the vector, I'm sorry, the embeddings, the 1,536 unique floating point values that represent the multidimensional space, and then stored that in a local database so that I could query against it, didn't have to hit OpenAI every time I needed the information. Then took those 1,536 dimensions and whittled it down to 2 dimensions to display here. And then in the next one, I'm going to show it in 3 dimensions, just to help with the visualization of what's going on in vector space. So let's take a look at what things look like in 3D. So again, transforming things into a 3-dimensional view. And then you'll have to kind of, think about how, as we've gone from 1 dimension to 2 dimension to 3 dimension, we're starting to see how these collections of words are related to each other. And you'll have to kind of try to imagine what that means in much higher dimensional space. But you can assume that we've gotten this much more value going from 1 to 2 to 3 dimensions. Going to much higher dimensions is going to give us the ability to slice and dice the meaning of the context of the words more easily. So now you can really see that locations are grouped together, that animals, in the right position are kind of grouped together, common objects are grouped together. And you can even now start looking deeper into those. Let's see what I can do here with common objects, where book and mirror are far apart, or phone and car are far apart. So there's probably some meaning embedded in there too, in the how far apart the these things are within their own groupings. You can also see, for some reason, I guess I turned that off, but I had emotions and colors overlapped quite a bit. And that's interesting because we often represent emotions as colors to be able to see that. Any questions before I move on to the next topic? Okay.
So guys, if you have any questions, please post them in the chat for now. And at the end, I will allow everyone to unmute yourselves and we will also talk in spoken. But for now, please use chat.
Great. So that's for words. That's where positioning, we're using a pre-trained model from OpenAI to position words in this multi-dimensional space. That's great that we can do that with words. But if you remember back at the beginning of in the deck, we're talking about retrieval-augmented generation and using chunks of data, sentences and documents. How do we translate what we're doing with words into sentences or document embeddings, right? So let's go into that. And we can basically do the same thing with sentences or documents, or really with chunks of data. And I'll explain what I mean by chunks of data in a minute. But we can then put those chunks of data, those sentences or documents, we can understand the meaning of those larger pieces of text and put them through the embedding process as well to encode the meaning of the sentence, not just the word in the sentence. And then that becomes pretty powerful for the RAG process to retrieve similar chunks of data for what we're looking for in the question we're asking the large language model. So let's go through this a little bit. So I can take a sentence, sentence embeddings capture the overall meaning of a chunk of text, and I can run it through the embedding process, and there you go. I get that 1,536 floating point values again that represent the meaning of this sentence in that multidimensional vector space. So the benefits of that are that we can now encode larger pieces of text and understand their meaning, their embedded meaning, and put that in a vector database. So we can store chunks of text along with their embeddings in a vector database, and then perform queries against that data to find similar information and return that. So the way that this is done is, you gather your documents. For this example, I'm going to use the Scrum Guide. It's a 13-page PDF, but it's also available as an HTML page. So that's what it looks like. It's a document it's just pretty concise. It's got some decent information in it. That's the good news is it's easy to kind of manage and deal with for this demonstration. The bad news is I think that ChatGPT has evolved well enough where it could actually return really good results without me going through a RAG for this. But just if you extrapolate the ideas here, you'll understand how the RAG process could be used to add value. So I'm going to take the Scrum Guide. I'm going to chop it up into chunks. So it really makes sense to have similarly sized chunks of data to be used in RAG, so that I'm going to go with 1,500 characters with a 200 character overlap. So 500 characters with a 200 character overlap. So 500 characters overlapping the previous one by 200 to make sure we're not losing any context at the boundaries of the chunks of text. Run the embedding process against all of those chunks, and then store the chunk along with its embeddings in a vector database. We can then use a similarity search against that to pull back information that's similar to a question that we're asking. So let's first pull down the Scrum Guide, a little bit of, there's a Python library called Beautiful Soup that will pull in HTML really easily. We'll take a look at the first 1,000 characters of the Scrum Guide. If we go back and compare that to this, you can see that, the 2020 Scrum Guide trademark, the HTML version, this HTML version is exactly the text that we have there. So now, let's see how many characters that is. So we have 24,000 or so characters. Let's break that up into those 500 character chunks with the 200 overlap. So we end up with 82 chunks of data from the Scrum Guide. And you're going to see each chunk is a little less than 500 because I went through a process to remove new line characters. So I stripped out a few characters here and there. And if I hadn't done that, it would have been 500. And here's what a couple of chunks or a few chunks look like. Right? So here's the beginning, and here's a 300 or so characters down, and so on and so forth. So we've got all of these different chunks. We can now take those chunks, first defining another vector database called vector store to store the results in. We can generate embeddings for all of those chunks of data. Here's an embedding of the first chunk. So that's what that looks like. And we can see that we have that 1,536 dimensions again. So we took that chunk of text, so we took the 82 chunks of text and ran the embeddings against them. So now we have these chunks of text, like the words we had before, positioned in this multi-dimensional space so that we can find similar pieces of data within the database. So now, getting into what the RAG pipeline is doing, we've got a question. In this case, I'm going to ask, what are the product owner accountabilities according to the Scrum Guide? So that's a question I want an answer from. I'm going to put that into and run an embedding against that, and then look for similar text to that question from the vector database. So I was going to say, go out and look in the vector database and return chunks of text that are similar to this question, and then combine that. So combine the question with the retrieved text into a full prompt, pass that over to OpenAI, and get a response. So that we're now using those chunks of data that's stored in the vector database to augment our prompt, to add additional information and context to the prompt so that the LLM can use that in generating its response to our question. So let's run that question just against a regular ChatGPT query. So this is not using RAG. And here's the response that we got back. I'm saying, what are the product owner accountabilities according to the Scrum Guide? It returned what looks like a really reasonable response. It's got 7 different things that the product owner is responsible for. But now let's take a look at that same kind of thing using RAG, where we will ask the same question. We'll position that in vector space, pull the similar chunks of text, which it retrieved the 6. I asked for 6, pulled back 6 chunks of text that are similar to that question. Here they are, and each one, it's got mention of things like, what you would expect, product owner, accountabilities, accountability, product owner. So very similar kind of information to what I was asking for. So we can take the question, we can combine it with these chunks of data that we pulled from the vector database. But there's one missing piece, and that's we need some instructions to provide with that. So there's some prompt instructions. This is a pre-made prompt instruction that I stored, and that says, you are an assistant for a question answering task. Use the following pieces of retrieved content, so the chunks of data, to answer the question. If you don't know the answer, say that you don't know. And then there's a spot to put in the question. So there's the question, and this will be replaced with the question. And then the context gets dropped in here. Those are the 6 chunks of data that we pulled. And we can use a pipeline. I'm not going to go through all of the steps of this. We can use a LangChain pipeline to run through the process of combining all of these things together and feeding it to OpenAI using GPT-4o mini and get a result. So here's the response based on that. It's pretty quick. So according to the Scrum Guide, the product owner accountabilities are listed here. It's more concise, right? So if I can compare that to, I stored the results of the previous query that were directly to Open AI, and it's a more concise version. And it's debatable whether it's better or worse. But what I'm really only trying to demonstrate here is how you can use a vector database to store that relevant data, pull what you need when you need it, and inject it into the prompt so that you can get better results. There does seem to be, from the testing that I was doing, it seems to be faster as well. So I get back the results from OpenAI when I've included that extra data faster than if I just give it a blank question. And so that's the RAG process. We'd run through another example. What are the benefits of Scrum? We can get that from a direct query. See how long it's taking. It's taking a minute to process what the benefits of Scrum are. It's come back with its response. And now we can do the similar thing using a RAG process, using the same question. The results came back faster. I can then format that in Markdown so you can see it. Again, debatable whether the results are better or worse, but overall, that's how the RAG process works. And I appreciate everybody's time for listening to this, and then open it up to any questions that people might have.
So thank you so much, David. Let me allow people to unmute yourselves and to start your videos. Guys, feel free now to ask your questions or give your comments. And Ken, you had a question that I decided to postpone. Now it's your time. Can you go ahead and ask any questions you have, Ken? And then I will ask other folks from the group.
Yeah, I think we lost the context on that one, but when we were going over the motion and colors example,
Yeah.
how are you able to see that a color and an emotion are related? Is it just proximity?
Yeah, I didn't. I for some reason emotion wasn't returned. Let's see what I did wrong here. I might have not had it in the list.
In the meantime, a participant is saying a very useful presentation. Thank you. And then John.
Hi, I just cannot turn on my video for some reason.
You,
I don't know. It says you cannot start your video because the host stopped it. So that's fine. I can ask the question though. It's at first, David, like to say thanks. It's a very clear explanation of yours. My question is, so you demonstrated a RAG, a non-RAG response, and then a RAG-based response.
Yeah.
Does that mean that the RAG-based response is 100%, the data coming from the RAG-based response comes from the document, from the PDF document, or it's a mixed? It's a
mix. So when you pass it to a large language model, I used the same color, sorry. It will take the added context into account, but it's going to combine it with all of the other information that it's been trained on as a large language model as well.
All right, gotcha.
So it's a combination.
Okay, great, thank you.
All right, so Ken, to answer your question, so if you look at colors and emotions in this 3D space, they tend to blur together, and I think that's natural, right? I think it's because we use colors so often to represent emotion, so that's That's what I was talking about when I said that. I just didn't have emotions graphed so that you can see them now.
Okay, so for example, blue would probably be somewhere near sad or something, right?
I can't guarantee it, but yeah. Let's see. Can we find sad and blue? Well, here's blue and there's nothing around it. So,
There you go.
but yeah, I mean, here's sad. Sad is near gold. So, I mean, this is again, we're mapping all of those dimensions down into three. So
Okay.
we're losing a lot in doing that process.
Yeah, you're losing a lot of information. There may be other dimensions that those things are related among. Okay,
Yeah,
got it.
I would expect so. I think if we were to run a query in higher dimensional space, we would find that blue and happy are close, or blue and sad are closer together.
Yeah, so one other question I had, I'm just trying to step back and think about the overall context of what it is that we're doing and why we're doing it, right?
Hmm.
So we are basically, I mean, ChatGPT by default has a large, obviously, model of things that it
Yeah,
is using for the prompts that we're doing.
yeah,
Sounds like what we're doing is saying, here's a specific here is a specific source or context that we want you to bring in
yeah.
and rely upon that more than just the default chat GPT. So they're trying
Yeah,
to
or rely on it in addition to everything else, but yeah, maybe give it more weight.
give it
I
more
think
But
weight.
I think a
if I,
perfect use case is a customer service chatbot, right? Where you've recorded all of your questions and answers over the years from interactions with customers, and you have this vast amount of data that you can then put through this process and make available to a chatbot to know that, okay, when somebody asks this question, here are the answers that were given, and be able to return a really relevant answer. And OpenAI is not gonna have that proprietary, really domain specific data. It wouldn't have been trained on it, and it won't be able to answer those questions. But if you pass in, 10 or so chunks of data to include, then you can get really good answers out of it. So I think this is in ways really, really great. And a lot of AI startups are founded around using RAG and similar tools to augment the chat GPT functionality and to create unique products.
Okay. So you're pulling the local context in,
Yeah,
using data that you want to use in order
right.
to derive better answers related to what you've got.
Yeah, you can also, with the addition of something called tool calling or function calling, where you predefine an API that OpenAI can have access to and how to call it. OpenAI can return a call to an API and go out and get some live data and then return that to be used in a similar way. So that's pretty powerful. You want to know, I'm planning a trip. What's the weather going to be like in the destination I'm going to? It can go out and pull that, 10-day forecast and return that, which, Chat GPT isn't going to know. Yeah, Natalie.
so guys, two things. One is I have a question in the chat. Bala says, thanks for the nice presentation. Whether this example notebook can be shared to understand in detail later. My understanding is whether this recording will be available for viewing later. Yes, it will. We are going to upload the recording to YouTube channel. And if you guys came here through Meetup, we will post the link in the comments section under the event. You will be able to find it there. It will take us a couple of days to process and upload the recording. Secondly, Ken, I also was wondering the same question, and our clients, already 2 companies at this point, have asked us this question. Hey, can you help us with the customer service, where we have a client in travel industry, and a lot of bookings are done through the website, and many bookers, they call customer service with some questions. And right now it is a very heavy load on the customer service. So the client is asking us, is it possible that you create an assistant where AI would be searching through our own knowledge bases or databases to help with the answer, either to the user themselves, it might be through a chatbot functionality, for example, or as a help for the customer service agent who are on the call with the client, with the user, and they're trying to find the answer not from the internet so much as it is from the internal knowledge bases and databases. And then we have another client who also approached us with a similar request. Hey, can you help us with implementing chatbot functionality where the chat would be able to provide answers from our internal knowledge bases?
Yeah, those are perfect use cases for RAG. Yeah.
More questions?
And I'm happy to share the Jupyter notebook. I don't know exactly how to do it with Meetup, but maybe I can drop it into GitHub and then share a link in the Meetup.
In the comments, below the event. How much of the response is based on local data? Can we specify weights to make it more relevant? Great question. I like it. What do you say, David?
Yeah, I think in the prompt, so the instruction, remember when I generated I haven't tried this per se, but when I generated the prompt instruction here, right? You could say something along the lines of give more emphasis to the context that I'm passing in than what you know, or something like that, to boost that. Or you could say if there's no information in the data that I provided, then use your own knowledge to fill in the missing blanks, or something along those lines.
It's through the prompts, how you structure the prompts.
It's how you structure this kind of instruction prompt that'll include the question and the chunks of data.
And it's quite reliable, his GPT judgment on how to approach your instructions, right?
Yeah, and then you get into prompt engineering and tweaking things to get the results that you want. But I think there's probably different ways that you could influence the chatbot to give you the results you're looking for. Yeah.
Ken is interested in the question of security. Is the data pulled in secure and / or isolated? What would it take to make sure it is secure, not shared?
Yeah, I mean that's one of the things that is a concern. There are open source models that you can use to run locally or run in your own environment. You're not going to have ChatGPT 4.0 or that level of quality, but it's pretty close. And chatting with a buddy of mine the other day, and they're doing it in a kind of secure way and really happy with the results they're getting, and they're using kind of more they're using models that they can run in on their own in their own data center. So yeah, it's doable, but there's some limitations. It's super easy to do it this way. I mean, there's just so many Python libraries that make it easy. But if security is a concern, you can definitely run it yourself.
So guys, we're at the end of the hour. We still have several minutes left, and there is yet another question. Questions are important. Being a complete Ken, go with it yourself.
Being a complete neophyte. Do you have any good references for prompt engineering? I need like a 101 or 102 reference.
Yeah, I have these resources here.
What's that?
I have these resources here. 3 Blue 1 Brown does an amazing job. He's got YouTube videos. His animations are out of this world. Really great resource to kind of get a deeper understanding of how neural networks work. These aren't necessarily the best resources for what you're asking for, but there's There, I can put these links in the meetup as well. There's some other good resources here for understanding word embeddings and vector databases that I can share.
But
There's
also, if we're talking prompt engineering specifically,
prompt
can
engineering.
a presentation that David did about a month ago was
Yeah.
specifically on prompt engineering, and I think it was a 101 actually. It was a prompt engineering
Yeah, it was.
for beginner level. It might be a good point to start, I think.
Yeah, and we shared that. Do we have that video?
We do have it. Yeah, we do have
Yeah.
it. It's uploaded, and I will also share it in the meetup event. And Ken, I will share it on LinkedIn, so you will also see it from there as well. The previous one.
There's some really cool prompt engineering techniques that you can use, and I outlined quite a few of those in that last talk, and happy to kind of pull together some other resources and share them as well.
Christopher is complimenting you, David.
Oh,
Christopher
it's very nice.
is saying thank you
Thanks,
for a
everybody.
great talk.
Yeah,
You
I
did
just want
an
to say
awesome.
thank you.
Go ahead, Chris. Yeah.
Yeah, no, it's awesome. Definitely something to learn from,
It's
and
pretty
being able
cool.
to take
Yeah.
complex subjects and being able to present them. I loved it. Thank you.
Yeah, great. And there's a lot more there. I couldn't pack it all in into 45 minutes or so. There's a lot of stuff out there to take.
Hopefully we will do another one maybe in a month. If it's an interesting subject, it looks like it's a hot subject, maybe we will do another one a month from now. I will post it. Let's see.
Great.
Thank you guys so much. Thank you for coming. And of course, thank you so much, David. Let's keep in touch through Meetup mostly. This is where we post the announcements about the events, and also in the comments, the recordings and links. You can also ask any questions through Meetup again, and request for topics that would be of interest, and then we will see who would be the right person to invite on that topic. Let's talk how we create amazing and up-to-date products through the Meetup group. Thank you.
Great. Thanks, everybody.
Thank you so much. Thank you, guys. Let me
Bye.
stop the recording.